Hi, everybody. Today we're looking at verifying trigonometric identities, and this is my absolute favorite trig topic. Now, the problem with this is really not a topic that you teach. Yes, I can show you how I work trigonometric identities and stuff like that, but you're really not going to learn the concepts until you get down and try these trig identities on your own. You need to get used to seeing what happens throughout problems to try to show one side of the equation is equal to the other. There are some common things that I'll mention in this video that you look for, but in practice, you just need to start working these on your own until you get comfortable with them. So, like I said, the topic of this section, there's really the one goal. It's to use fundamental trigonometric identities to verify identities that are not our basics. Now, our fundamental trigonometric identities that need no verifications are these. We know the reciprocal identities, the quotient identities, and hopefully by now you also know the Pythagorean identities. If not, it would be wise to commit those to memory as well. So sine squared plus cosine squared is 1. And remember, along with that one, you should also keep in mind, so 1 minus cosine squared is sine squared, and 1 minus sine squared is cosine squared. All three of those would be helpful. For the second one there, 1 plus tangent squared is secant squared. So you can say, okay, that's an identity. How about if I solve for tangent squared and say tangent squared is equal to secant squared minus 1? That might also be helpful. You might also need secant squared minus tangent squared is equal to 1. So any iteration of these three identities sometimes is helpful. This last one, it's not used as often, but 1 plus cotangent squared is cosecant squared. And of course, keep in mind, you could also solve for cotangent squared and say, well, cotangent squared is cosecant squared x minus 1. All right. Our even and odd identities, remember that the cosine and the secant are our even functions. All other four trig functions are odd, which means the function evaluated at negative x is equal to the negative of the function evaluated at x. You can see sine, cosecant, tangent, and cotangent are all odd functions. The cosine and the secant are the even functions, where you can change the sign on the angle and it doesn't do anything to the sign of the cosine or secant function. Now, when we verify identities, we're going to show that one side of the identity can be simplified so that it is identical to the other side. Each side of the equation is manipulated independently of the other side. So what I will always do, I'm going to pick a side, either the left or the right-hand side of the equation. And the choice as to how I decide to which one to pick is I always pick the more complicated side. Now, after I pick that more complicated side, I work with it algebraically or using trig identities to show that it's equal to the remaining side. For example, so if I'm asking you to verify the identity, cosecant x tangent x is equal to secant x. Okay, so clearly the left-hand side of this equation is more difficult. That's the part I'm going to work with. So I can say, well, I know cosecant times tangent is the same thing. Cosecant is 1 over sine. Tangent is sine over cosine. Now, when I do that, I can already see, ooh, I'm going to have some simplification here. Sine x in the numerator cancels with sine x in the denominator, and this is going to simplify to be 1 over the cosine of x. And fortunately for me, we know that the 1 over the cosine is one of our basic identities. 1 over the cosine is the secant, and that's precisely what we needed to show. Now, oftentimes, in order to show the reader that you're done with your verification, you put a little check mark over the equal sign at the very end. So when I show that the left-hand side is equal to the right-hand side, you don't have to, but it's probably wise. And I did it on all of my homework problems just so you could tell when the problem was done, put a little check mark over the equal sign. Now, for the next one here, I ask you to verify the sine of x minus the product of the sine x cosine squared x. Let's show that that's equal to sine cubed x. Okay, pretty easy. you look at the left-hand side and you automatically know, well, I don't want two separate terms there. I just have one term on the right-hand side. So I'm going to go ahead and factor the greatest common factor out of those two terms. I can factor a sine x out. When I factor that sine x out, it's going to leave me 1 minus cosine squared. Well, that's one of our fundamental Pythagorean identities. Sine squared plus cosine squared is 1. 1 minus cosine squared is sine squared. So I replace 1 minus cosine squared with sine squared, and then I can say, well, sine times sine squared is my sine cubed x, which is precisely what we needed to verify. Done. Now you're looking at this one saying, ooh, this one's more beautiful. Well, it is. We have well, I started to call it a rational function. It's not a rational function because those are not polynomials, but we have the sine function divided by the group 1 plus cosine plus the group 1 plus cosine divided by sine. And our goal is to show that this is equal to 2 cosecant x. A lot of students would struggle with this one. Clearly, I'm going to choose the left-hand side of this equation. Why do I say clearly? Well, because the left-hand side is more complicated. It's easier to take something complicated and simplify it than it is to take something simple and try to make it to the more complicated side. So now, when I'm looking at that left-hand side, I can say, well, clearly I don't want two separate fractions. I need all of this to be one term. Then the only way I could ever add those fractions is to get a common denominator. So you'll see the very first thing I did here, I said, I'm going to choose the left-hand side and work with it. Now, how do I work with it? Well, that first fraction, in order to get a common denominator, needs a denominator of sine x. So you'll see I multiplied by sine x over sine x into that first fraction. The second fraction already had a denominator of sine x, but it needed a factor of 1 plus cosine x. So you'll see I multiplied the second fraction by 1 plus cosine x and 1 plus cosine x, and understood 1. Now, I can see the numerator also already had a factor of 1 plus cosine x, but please remember, it had to be multiplied by an understood 1 in order to get that 1 plus cosine x in the denominator. So now when I get my common denominator of sine x times 1 plus cosine x, I can say I'm going to leave that factored in my denominator. In my numerator, I multiply out. I'll have sine x times sine x is sine squared x. Between these two binomial expressions, I can FOIL them out and I'll get 1, and I will get plus cosine x for plus 2 cosine x. And then your last term would be cosine squared x. Okay, this is looking good. Now, I'll finish this on the next, well, maybe not finish on the next slide, but I'll continue it on the next slide. The only thing I've done from the bottom step on the previous page to the next page is I just said, once I get that common denominator, combine your numerator. So I have sine squared plus 1 plus 2 cosine x plus cosine squared. As soon as I see I have an expression, it has a sine squared plus a cosine squared, I'm going to go ahead and group those together. And now what is that going to become in my next step? Well, that's Pythagorean identity. Sine squared plus cosine squared is equal to 1. So now I have 1 plus the 1 that already existed in the problem plus my 2 cosine x. That gives me 2 plus 2 cosine x, and I've shown a lot of steps. You could have went from this step directly to this step without any trouble whatsoever. And now that you see you have this, you can say, well, hey, that numerator has a common factor of 2. I bet we should factor that out. You bet. I factor the 2 out, which then allows me to see that the remaining factor is in common with the denominator. So that group 1 plus cosine x cancels out, and I'm left with just 2 over the sine of x. That's the same thing as 2 times 1 over the sine of x. And I can say, well, 1 over sine of x, that's the cosecant of x. So this is going to equal 2 cosecant x. Is that what it was supposed to equal? Absolutely. Verified. Gorgeous. For our next one here, again, it's a similar type of problem. I have 2 fractional expressions with trigonometry in them, 1 over 1 plus sine theta plus 1 over 1 minus sine theta. And my goal is to make this equal the right-hand side, which is 2 plus 2 tangent squared theta. Okay, I'm going to work with the left-hand side. Why? Because it's more complicated. And as soon as I work with that left-hand side, I'm thinking, well, yet again, I'm going to try to get a common denominator there, and so I can add these two fractions together. So I take my two fractions. The first fraction is going to get multiplied by 1 minus sine over 1 minus sine. My second fraction already had the 1 minus sign in the denominator. It needs to get multiplied by 1 plus sine over 1 plus sine. So now you see, yes, I have achieved my common denominator of 1 plus sine theta times 1 minus sine theta. Now, in order to bring this all into one fraction, I bring my common denominator in my numerator. Well, that first one was 1 times the group 1 minus sine theta. That gives me 1 minus sine theta. I brought that down in this step. Then I would have plus 1 times the group 1 plus sine theta. So I'll have 1 plus sine theta. Now notice what happens in your numerator. The plus sine theta and the minus sine theta cancel. So we're just left with 1 plus 1 is 2 over this denominator. And now with that denominator, if I ask you to go ahead and FOIL that out, you just say, well, it's going to become 1. And because they're conjugates of one another, the minus sign and plus sign cancel, but then you'll have minus sine squared for your last term there. 1 minus sine squared, you need to remember, oh, that's one of our gorgeous Pythagorean identities. It's equal to cosine squared. So here on the next page, you'll see, all right, that left-hand side, and you don't have to rewrite all of this each time, but this is just showing you the progression from one slide to the next. That left-hand side, I said, was 2 over 1 minus sine squared theta, which now I'll say, well, that's the same thing as 2 over cosine squared theta. Why does that help? Because 2 over cosine squared theta is the same thing as 2 times secant squared theta. Since secant is the reciprocal of cosine, secant squared is the reciprocal of cosine squared. So I have 2 secant squared theta. Now, yet again, I'm going to use one of our trig identities. We know that secant squared theta is equal to 1 plus tangent squared theta. That's the second Pythagorean identity solved for secant squared. So secant squared theta is equal to 1 plus tangent squared. Well, think about what happens if you plug a 1 plus tangent squared into the place of secant squared in this verification identity. You would have 2 times the group 1 plus tangent squared. Now, if you distribute the 2 through that group, you're going to have 2 plus 2 tangent squared theta. Gorgeous. That's precisely what we needed to do. So we can say this identity is verified. Now, with this section, you're just going to need to try the problems, choose one side, and use some algebraic techniques, whether it's getting a common denominator, whether it's factoring, in order to get to an identity that you can substitute. Like in this one, I've used reciprocal identities, I use Pythagorean identities, and with a combination of algebraic skills with some basic trig identities that's mentioned on the first 2 slides of this section, you should be able to do these problems well. I worked all the assignment out of the book was 1 through 59 odd. Worked all of those problems, showing all of the steps, and had a lot of fun doing it. Please make sure you take a look at that if you need any help. And as always, ask me too. I'll be glad to help.